Good morning and welcome to 2.9. We are going to go ahead and work on some graphing of quadratics. We've kind of gone back and forth between the algebra, the diagrams, and now some of the graphing too. We've done that a little bit so far in this module, but we're going to look at some more of them. So we've not really seen this in terms of, we would call this number one, in terms kind of the side lengths, the area in terms of side lengths. And now what we're going to do is we're going to find the vertex, y-intercept, and x-intercepts of each of these functions. So what we're going to do first is we see this in terms of the side lengths again, like I said, but now we don't quite know what to do with that yet. You guys might, and I'll give you some tips right after this first one. But what I'll do first is I'm going to go ahead and put this into vertex form by first going from factored form to standard form. So I'll go ahead and FOIL this all out. So first, outer, inner, last, where I go 3 plus 3x minus x minus 3. Now, that should be x squared plus 2x minus 3. Now also, what this foiling does is this tells me actually the side lengths of this rectangle, so I can figure out what I need to do in order to make this thing a perfect square, right? We've completed the square a little bit, so I can say, okay, if I have 1x on either side, a perfect square would just be 1, right? So now I would say, okay, what do I have to do to this 1 in order to get me to this negative 3? And what I would have to do is I would have to subtract 4 more unit blocks, right? So if I'm looking at the factor, or not the factored form, but the vertex form, I can say, okay, this is my perfect square, x plus 1 times x plus 1, or x plus 1 quantity squared. But then to get it to this negative 3, I have to subtract 4. So the vertex will be at negative 1, negative 4. Now remember, when it's in parentheses, we change the sign. When it's out of parentheses, we do not. So the vertex will be negative 1, negative 4. We also have discovered that the line of symmetry is just the x value of the vertex. So I'm going to say x is equal to negative 1. Then I will go ahead and graph this to kind of get a picture of where the things like the x-intercepts or the y-intercepts are. You also actually would know the y-intercept will be this c term, because if you plug 0 in for x, 0 in for x, you've got 2 times 0 and 0 squared, which are both 0, and the only thing left over is negative 3. So the y-intercept would be 0, negative 3. That's all good. So let's go ahead and plot this vertex and then plot the parabola. So I'm going to just pick axes right about here and then plot the vertex at negative 1, negative 4, right here. And then as I do, I will go from the vertex over 1 and up 1, because 1 squared is 1, then over 2 and up 2 squared, which is 4. Also, I've noticed I have no stretch on this. Over 3 up 9. Over 3 up 9, because 3 squared is 9. And here is my parabola. Now look at this parabola. So check out its x-intercepts. We can actually see them right from this graph, right? We see them at 1 and negative 3. So I could say my x-intercepts are at 1, 0 and negative 3, 0. Now if I look back up at this factored form of the equation, what I can see is I have a negative 1 right here and a positive 3 right here, but my intercepts are positive 1 and negative 3. So how did I go from x minus 1 and x plus 3 to intercepts of being positive 1 and negative 3? Now, you might get a hint from our vertex form, how we've said if there's something in parentheses, we can change, we negate it, and that's what we do when we pull it out of parentheses. The same is true for factored form when we're looking at intercepts. It's no coincidence that x minus 1 gives us an intercept of 1, and x minus 3, or x plus 3, gives us an intercept of negative 3. Now, algebraically, what's happening there is what we did before to figure out what the x or the y-intercept was, is we plugged in 0 for x, right? Up here in this equation. Now, in order to figure out what our x-intercepts are, algebraically, we can plug in 0 for y. So we could say 0 is equal to x minus 1 times x plus 3. So if I saw these two binomials, I could actually go, I want to solve for this first one, so I'm going to divide both sides by the second one and see if I can get that first one by itself. Now, 0 divided by anything is just 0. So what I do is that cancels on the right side, and I get 0 is equal to x minus 1. Add 1 to both sides, add 1. My x-intercept is 1, right? Now in that same fashion, if I try this over here, and I say, I want to divide out the x minus 1 this time, and I want to figure out what that other term is, I can also do that. Divide both sides by x minus 1. 0, again, divided by anything is still just going to be 0. They cancel out over there, so I have 0 is equal to x plus 3. Subtract 3 from both sides, and I get negative 3 is equal to x. So there's my other x-intercept. Now, that's the basis of what we're doing. A shortcut is when we have factored form, you can take each factor, set it equal to 0, and solve for x. Set it equal to 0, and solve for x. Okay? So that'll be the shortcut. So now let's try that for our next function, where we have even this multiplier, but even if we divided that multiplier out, we would still get 0 divided by 2, which is still just 0. So I can set each of these equal to 0 to solve. So now we're going to actually go from our x-intercepts first, and then try to figure out what's going on with the rest of our function. So if I do that, I can say x minus 2 is equal to 0 and x minus 6 is equal to 0, where I add 2 to both sides, and I get x is equal to 2, and over here add 6 to both sides, so x is equal to 6. My x-intercepts then are 2, 0, and 6, 0. So I'll go ahead and just plot those on this graph right over here. At 2, 0, and 6, 0. Now, I can see that, I know from previous lessons that my vertex should lie on the line, the axis of symmetry, which should sit right directly between those two x-intercepts. So I should have, since there's just each 2 away from this point right here at 4, I can say that is my axis of symmetry, or line of symmetry. So I'll go ahead and say x is equal to 4 for that line of symmetry. Now where the vertex is, now I can either try to count this, but I have a stretch of 2 and that complicates things a little bit. So instead of trying to count it, what I'll do is I'll take my line of symmetry, which is the average of my x-intercepts after I've already solved for them, right? Not while it's negative 2 and negative 6, but after I've solved for them. And I will take my line of symmetry and plug it back into the original equation of f of x is equal to 2 times, and now I'm going to plug in 4 minus 2 and 4 minus 6. What I'll do is I'll solve for this f of x, or y functionally, and what I can then determine is if this is the x value, the line of symmetry at x equals 4, of my vertex, this computation is then solving for the y value of my vertex. So I have 2 times 4 minus 2, which is 2, times 4 minus 6, which is negative 2. So I look through this multiplication, 2 times 2 is 4, times negative 2 is actually going to be equal to negative 8. So my vertex will be at 4 from my line of symmetry, comma, negative 8 for my computation. So I can go ahead and plot that point right here. And now I have this stretch of 2, so my point should go over 1 and not up 1 squared, which is 1, but instead over 1 and up 1 squared times 2, which is 2. Okay, and then if I look at these x-intercepts that are coming, if I go over 2, normally I would go up 2 squared, which is 4, but now I go up 2 squared, which is 4 times 2 because of that little multiplier, which is actually 8, right where these two x-intercepts sit. So then I just connect poorly, I might add, my dots up there. And there you have your parabola. It's facing upward. It has a stretch of 2. The y-intercept, I'm not quite sure where it's going to cross because there's a lot of upward movement here before it's going to cross the y-intercept 2 to the left of where I am currently. So what I'll do is, just like we did before, I'm going to plug in 0 for x to determine what my y-intercept is. So I have f of 0 is equal to 2 times 0 minus 2 times 0 minus 6, which I get 2 times negative 2 times negative 6. 2 times negative 2 is negative 4 times negative 6, which is a negative times a negative, so it will be a positive, and negative 4 times negative 6 is positive 24. So my y-intercept is way up there, 0, 24. All right, for this next one, I would like for you guys to try this one on your own. Remember that kind of logical piece that I had up here where you divide each side by one of the terms, and then you have 0 equals the other term. I want you guys to try that one on your own. For right here, pay attention carefully to this negative sign, and solve for those x-intercepts, and then try to find your line of symmetry, find your vertex from the line of symmetry, and finally find your y-intercept. All that being said, go for it, and then we can talk about that on Thursday if you guys would like to, and we'll go from there. So hopefully that was successful for you. And now we can look at 4, A, B, C, D, and E, where we used those examples previously, and I kind of hinted at the answers to some of these, but basically we'll just answer formally each of these equations now. So how can you use the quadratic function in factored form to find the line of symmetry? Well, what did we do? If we look back up here, once we found the x-intercepts, we took the average of those x-intercepts, right? The line that is directly between those two x-intercepts, and that was our line of symmetry. So it is the average of the x-intercepts. The next one, find the vertex of the parabola. Well, once we found the average of the x-intercepts and set it equal to x, we can use that that line of symmetry to find the y value of our vertex. So we'll use our line of symmetry value to plug in and solve for x or for y. And that will be directly between those x-intercepts. That's how we'll find our vertex. Okay, find the x-intercepts. Well, we'll set each factor, is what we'll call it, equal to 0, and solve for x. There we go. How to find the y-intercept? Set x equal to 0, solve for y. And really what we were doing up above is when we set each factor to 0, we're saying y equals 0, substituting in y equals 0. And then finally, to find the vertical stretch, that is just whatever multiplier is in front of the x's. Coefficient, multiplier, coefficient. Is in front. All right, so there are the first 4 questions, and now we're going to do something a little bit different. And I want you guys to start this, and then I'll give you an example. So you are going to choose 2 linear functions and write them in the form of f of x equals m, which m is the slope, times x minus c. So m is the slope, and x minus c are just some numbers there, okay? So I want you to go ahead and try writing those, and then also try graphing those. So pick some numbers that are relatively small so that you can graph them on this coordinate plane. And then we'll come together in just a moment and graph those together. Okay, so here are the two functions I'm going to select. It'll be 2 times x minus 1, and let's do 1 times x plus, let's try it plus 3. And I'm going to go ahead and graph those right over here on this coordinate plane. And I'll say, if I were to put this in slope-intercept form, right, this would be 2x minus 2, and this would be x plus 3. So I know that the slope of that first one will be positive 2, and it's going to go through the point negative 2, or 0, negative 2. Slope of rise of 2, run of 1, rise of 2, run of 1, and so on up there. Same thing back down here, and so on down there. So there we go. It crosses the x-axis right there at 1. Now this next one is a slope of 1 at x plus 3. So I know that the y-intercept would be at positive 3, and slope of 1 is just a perfectly diagonal line, right like this, and continuing on up. They'll cross eventually up there. That's just fine. I can also notice real quick that x-intercept is at negative 3, which is intriguing. So now what we're going to do is, on the same graph, I want to write the new function, which is actually the product of those two linear functions. So if I do that, I'll have 2 times x minus 1 times 1, which I don't really need to include, times x plus 3. Now, what shape is created? Well, that looks awful similar to what we just had previously up here, where we had all of those different x-intercepts, and we got parabolas, right? So if I look at this as a parabola, I can say, here's one x-intercept, here's another x-intercept. So that actually, oh, look at that, is right there and right there. So the axis of symmetry should be the average of those x-intercepts, which, let me just write those down, are 1, 0, and negative 3, 0. So to find the average, I'll need to do negative 3 plus 1 divided by 2. So that should be negative 1 is the axis of symmetry right here. So I can go ahead and plot that down. To find the y of the vertex, I'll plug that negative 1 in. And I get 2 times negative 2 times positive 2. 2 times negative 2 is negative 4 times positive 2 is negative 8. So my vertex is going to be at negative 1, negative 8. So I'll come down 1, 2, 3, 4, 5, 6, 7, 8 right there. Now look at this. I have a stretch as well. So instead of over 1 up 1, I'll go over 1 up 2, 1 squared times 2, and then over 2 up 4 times 2, which is 8. And look at that. It goes right through those x-intercepts again, which that is very intriguing. So the x-intercepts of the parabola are actually also the x-intercepts of those two linear factors of my quadratic function. So if I describe the relationship between the x-intercepts of the linear function and the x-intercepts of the function p of x, which is this second one down here, p of x equals, what could I determine? Well, I could see that actually the y-intercept is, interestingly enough, if I look at the y-intercept too, it's even correlated. So the x-intercepts are the same. Let's go ahead and write that down. X-intercepts of the parabola are the same as the x-intercepts of the lines. Or linear factors. And then, if I look at this y-intercept, I have a y-intercept of 3 and negative 2. Well, look at where my parabola's y-intercept is, negative 1, 2, 3, 4, 5, 6, which is negative 3 times negative 2. So what I could say is the y-intercept is the product, is equal to the product of the linear function's y-intercepts. See, that apostrophe belongs on the outside of that S. There we go. So that is quite an interesting piece of information. Here's from previous years, but we don't need that because we picked some new functions. So now what we could say is describe the y-intercepts. Oh, we already did that. Whew. Look at that. The y-intercepts are multiples, right? So the y-intercept of my linear functions multiply to the y-intercept of the parabola. That's fascinating. Okay, number 9. Given the parabola to the right, sketch 2 lines that could represent its linear factors. So the things that we need to pay attention to are that the the y-intercepts have to multiply to -3, and the x-intercepts have to cross at -1 and 3, right? So there are a couple of different things we could look at here. It could be a really simple line of just x plus 1, and let's say -3x, or excuse me, x minus, no, plus 3. Look at that. Because it goes through both of those intercepts. The y-intercepts multiply to -3, so that can work just fine. Another thing I could do is I could say, what if this line instead, this would be a little more complex, but what if this line goes through -6 down here and 3, right? So it's going all the way like that. And then instead of, if it goes through -6 and 3, then it would have to go through 1/2 and -1, right? So I could have lines that look like that with pretty varied slopes. Either one of those would work just fine. I'll go ahead and use this second one just for fun. So what we have is 1/2 x plus 1, because the y-intercept is at 1/2, right? So if I were to multiply this through, that 1/2 would be right there. And then I have a slope for my second line of 2x plus, or minus rather, 6. Or 12, because the x or the y-intercept would have to be 6. So when I multiply that through, oh goodness, no, 3, because when I multiply that through, it'll get to 6, right? So there are some factors. Oh my goodness, look at this. When I multiply those, I get 2 times 1/2, both out of those parentheses. So 1/2 times 2, which that is just 1, right? And then times x plus 1 and x minus 3. Now, if you picked any set of lines that satisfy these qualifications, we would end up with lines that, or with 2 factors that simplify to x plus 1 times x minus 3, which are these x-intercepts of the parabola, right? So again, we use the x-intercepts, had to cross at the x-intercepts. So the lines had to cross, or had to have the same x-intercept as the parabola. And the y-intercepts, parabola, and the y-intercepts had to multiply to the y of the parabola. So number 12, are those the only 2 lines? Well, I've showed you already now 2 sets of lines that could satisfy this parabola. So it's not the only 2 lines. We could use a myriad of lines. But as we go ahead and combine those, as we did right up here, this can actually be the answer to number 13, to say, you know, I simplified those equations out when I multiplied the 2 factors of my lines, and they came out to being x plus 1 times x minus 3, giving us the parabolic x-intercepts of positive 3 and negative 1, with the y-intercept at negative 3, which you can also see 1 times negative 3 is negative 3. So that gives us that y-intercept, which is very intriguing. Okay, that's all we have for 2.9. You can go ahead and work through 2.9, read the instructions all the way. If you have any questions, we can talk about them when I get back to class.